Part 1. Before proof. Around 1800 BCE, somewhere in Mesopotamia, a student pressed a reed into a palm-sized disk of wet clay. He drew a square. He drew both diagonals. Then, along one of them, he wrote a number. The tablet survived. It sits in a collection at Yale today, cataloged as YBC 7289. And the number scratched along that diagonal is its length accurate to about 6 decimal places. Whoever taught that student knew the value we now call the square root of 2 to a precision that would satisfy a modern engineer. They knew it 4,000 years ago, in a city of mud brick, using a system of numbers based on 60. And they had no idea what they were holding. Their number was very, very close. It could never be exact, not with more clay, not with more patience, not ever. But nothing in their mathematics could have told them that. The question did not have a shape in their world. They had found the diagonal the way you find a stone in a field, by handling it, weighing it, getting to know it. They had not asked what it was. This was not a failure. It was simply how mathematics worked for most of human history, across most of the world for thousands of years. It was a collection of things that worked. And they worked beautifully. Egyptian surveyors could restore the boundaries of a farmer's field after the Nile flood erased them. Babylonian scribes could solve problems we would now write as quadratic equations, and they could do it in their sleep, following procedures memorized from tablets. Take the half, square it, add, take the root. Do this, and the answer appears. A recipe. Recipes do not explain themselves, and nobody asks them to. Nobody wrote, on any surviving tablet, the single most important word in this book. Why? Then, in a scatter of trading cities around the Aegean, somebody did. We do not know exactly who or exactly when, and the Greeks themselves later invented tidy legends to fill the gap. But over the course of a few centuries, a small number of people did something genuinely without precedent. They stopped asking what the answer was. They started asking how they could be certain. Out of that question came proof, and proof is the strangest thing in this book. It is a way of arguing so tightly constructed that it closes a question permanently. Not for now. Not until better instruments come along. Forever. Every other kind of human knowledge is provisional. Laws get repealed, empires fall, scientific theories are overturned by better ones. A theorem, once proved, stays proved. Everything Euclid established still holds, and will still hold when the sun burns out. Nothing else we do works like this. It was also dangerous, in a way its inventors never anticipated. Once you can prove that something is true, you can also prove that something is impossible. And the very first great proof did exactly that, to the very number on that Babylonian tablet. The diagonal the scribes had measured so carefully turned out to be unmeasurable. The most obvious line in geometry broke the world that had been built to contain it. That is the arc of this part. It covers more time than the rest of the book combined, from the last ice age to the Mediterranean, and for almost all of that span, very little happens. Then, in a few remarkable centuries, everything does. A crisis over a diagonal. A geometer in Alexandria who takes a handful of assumptions, so obvious they feel like nothing at all, and builds from them a structure that will stand for 2,000 years. And at the end, a man in Syracuse who comes so close to inventing calculus that reading him now feels like watching someone reach for a light switch in a room that has not been wired yet. It begins, as nearly everything does, with somebody trying to keep track of their animals. It begins with a scratch on a bone,